Previously, we looked at getting information into our Apex network. Now I'll be looking at the default scripts on the edit graph node. So I'll get an edit graph node. If we look at the parameters, we'll have a number of scripts here. There'll be two folders. The first will be general scripts, and the second will be rigging scripts. Most of these scripts will require us to refer to nodes which are external to the edit graph node. The functionality for all of these scripts is reasonably basic. I'll probably not be using many of these scripts in the future, as I'll generally try to script this functionality myself. But these scripts do give you basic functionality, and they are useful as references. The first script option here will be merge graph. This will essentially copy another network and it'll place it within this node. We also have an option for it to do this by creating a subnetwork within this network. If I press this, I'll get a dialog containing the directory tree. This will allow us to select a specific node. I'll go to one of my other Apex networks. I'll find an edit graph node and I'll select it. This will merge that graph with our current network. This graph should now be editable within my network view. So if I do this as a subnetwork, I can select the same graph, and we should get exactly the same result. The network, however, will now be contained within a subnetwork. The next script is also a very straightforward script. This is the import Sop Node script. What this will do is access a node which is a verb within the graph network. A verb is essentially the same functionality as a Sop node. If I open the tab menu within my network graph, we'll see that we have a Sop verb section here. This essentially contains equivalents of all the Sop nodes. So for example, I get an RK chains node. I can select my graph. I'll run the import Sop node script. I'll then get the interface to select my node, and this will bring in the RK chains verb. I can of course also get this through the tab menu. For the RK chains, we'll go to the Sop verbs, and this will be under the more options, and this will be under Sop KineFX RK chains. So we can reference this way as well. Although the easiest way is probably just to use the search option. In this case, typing in RK will bring up the RK chains node, and this is probably the fastest way of getting it. That will be the general script. Next we'll have the rigging scripts. I will not start with the import skeleton and update skeleton, as these are the most complex of the scripts. Instead, I'll start looking at the add set point transform node. When we use this, we will not search for geometry, as this will just give us the most basic network setup. This will add 3 nodes. It will add the input node and the output node, and it will connect these with the set point transforms node, which is the node which we will use to update the positions of geometry. So this gets in our geometry in the input, it updates it in the set point transform node, it then passes the result into the output node. This is a very basic setup, and is essentially a quick way of getting an input and an output. This primarily serves as a good example of how to set up a script network. To examine how these nodes work, we can actually look at the type properties. Under the type properties, we'll look at the scripts tab. All of these scripts are within the default Python module for this HDA, and you can examine them to see the functionality. I'm not going to go into any of this now. The next 2 scripts are actually the most useful, and these scripts rely on us having a skeleton. This, of course, is a KineFX skeleton and not a legacy system skeleton. There are numerous ways of creating skeletons. The most straightforward is the built-in KineFX skeleton node. The biggest advantage to this node is that it is beginner-friendly and will generate all the needed attributes while creating the rig. It also has an interface which makes it easy to draw out a skeleton. However, I generally will not use this node, and it will not be the main node that I'll be using. Instead, I'll construct my skeleton manually, and I'll start by getting a line node. The reason I prefer to construct skeletons manually is I prefer to have absolute control over the transforms. Essentially, all you're doing when rigging is manipulating transforms. The built-in nodes for KineFX create transforms. These transforms are suitable for when you're doing motion capture and are useful for retargeting, but are not necessarily good enough for rigging. And you generally are going to need some manual control over transforms when rigging in any case, so I prefer to take control from the start, so my transforms will always be consistent. So essentially how KineFX works is we'll have our geometry, and we'll turn the line into a skeleton by adding attributes to its points. So we have our line node, and we want to add some points to it, and I'm going to add 3 points to the skeleton. The first of the attributes which we'll need to add will be transforms. There are a number of ways of doing this. For example, we have a rig doctor node. This node has functionality that will allow you to add transforms to geometry, but I'll be adding transforms manually, and I'll do this with an attribute wrangle node. I will eventually want 2 sets of transforms, The first will be for my skeleton, and the second set will be for my controls. I'll only be working with the controls in a later video, but I'll start setting them up now. I'll start with the skeleton, and our transform will actually be the rotation. With KineFX, we'll get the translation from the point position. So our rotation will be a 3x3 matrix. I'll specify this with 3 at, and the name of the transformation matrix will be transform. We can set this between brackets. We can also use the set function. I'll use the set function. We could set all of our parameters here, but I'm going to specify this using 3 separate vectors. The first will be for my x-axis. I'll have a vector for my y-axis. The final vector I add will be for the z-axis. Of these vectors, x will always be the most straightforward. This is a standard unit vector in x. The x value will be 1. The y and z values will be 0. For the y value, I'm not going to set this as a default 1 in y. Instead, I'm going to set this to be -1 in z. My z-axis will be 1 in y. I can then use these values to set my transform, so the set function will be set with my x, my y, and my z. As all of these are unit vectors, I will not need to normalize them. I should now have my transforms, and I can try and visualize these using a visualize rig node. These joints are not yet bones, as they do not currently have a name, so the transforms will not necessarily show. However, we do not necessarily need these to visualize the transforms. I'll do this by activating my visualizations. Over here I can click on my transform attributes, and they should now be visible. I will want to update these visualizations, so I can edit my visualizations. And here I'll set the length to be 0.1. This is not working because I've made a typo. I've typed in Z for X instead of X. Our transforms are now working. We can see the transforms as well as the visualizations for the transforms. The reason I'm setting up the controls this way is that I want the Z axis to face down the length of the bone. By default, the bones in KineFX tend to work like this. Essentially, if we had a bone at the center of the world, by default this bone would look down the Z axis. 0 in the world would be the root for this bone. The bone would lie down the Z axis, and the Y axis would point upwards. So this would be the coordinate system for our default bone, and my skeletons will be maintaining this coordinate system for every single bone. Although it doesn't really matter what coordinate system you use, as long as it is consistent throughout the rig, and that you have consistent manipulation of the transforms. So I now have my orientation for the skeleton. The next thing that we require for a skeleton will be the names of the joints. To do this, I'll get a name node. For the skeleton, we'll need these to be point names. For the moment, I'm not going to use the name node, as with this node, I'll need to name the points individually. Here, I'm once again going to use an attribute wrangle node. The attribute will be called name, so this will be @name. I'll set this with the sprintf function. For the moment, the name for these will be point. I'll then have a wildcard with %s, and I'll set this with the current point number. We should now have names for our points. I can activate this for visualizations, and then I'll edit the visualizations. And now we should have a skeleton. Points have names, and they have transforms. This should now be capable of deforming geometry. So I'll get some geometry, and in this case I'll use a tube. I'll set the position of the tube to be half the height in Y. This should place the base of the tube at the center of the world. I'll reduce the radius of the tube, and I'll add more detail to it. We can now add weights to this geometry. To do this, I'll get a joint capture by a harmonic node. The mesh that we're going to deform will go into the first input. The skeleton will go into the second input. The animation will be set through the third input. In this case, I'll just use the skeleton. To animate this, I'll get a pose node and I'll connect it to the third input. To view this, we can get a bone deform node. This will be connected after I've added my weights. So this is how I would manually create the basic rig, and if I use the pose node now, we should be able to deform the geometry. One thing to note is for our final skeleton, we will not necessarily need the final joint. This joint is usually useful for calculating transforms. Essentially, I'd use it to calculate the orientation of the previous joint. So for example, I could edit this, and I could move our last joint. We could generate joints on this geometry using an orient joints node. This would allow us to calculate a decent transform for the middle joint. However, this calculation is only possible because we've got 3 joints. The final joint isn't actually needed for the deformation, but it's needed to calculate our transforms. So for our final skeleton, we do not actually need this joint. So here I can get a delete joints node, and I can add it after we finish the skeleton, and here I can delete the final joint. So this finishes my basic KineFX setup, and usually I'll have a separate branch for the skeleton and a separate branch for the controls. However, that is not relevant yet. What we want to do now, however, is get this network into our Apex node graph, and this will be generating points which we can use to control the skeleton. So once again, we can build this manually, or we can build this with a skeleton. And here we'll have some differences between the two methods when we try and add this to our graph. I'll generate a basic skeleton quickly so we can show the differences. I'll go to the front viewport and I'll draw out my joints. So essentially we could have a similar setup using the skeleton node, where the skeleton would set the second input of the weights and the deformers, and would connect animation to the third input of both of these nodes. So the reason for building both of these is if we build the skeleton manually, we'll have a different result from if we build the skeleton using the skeleton node. There are specific attributes which the Apex scripts are going to be looking for, which are added in the skeleton node, but are not actually essential in the creation of the joints. So to look at the differences, I'm going to get a null. I'll attach this to the end of my network, and I'll give this the name manual out. I'll duplicate this. This will be connected to my skeleton node. This will be called skeleton node out. This has given us a relatively long-winded interlude, but we can now use this skeleton to run our scripts. I'll press the import KineFX button, and I'll bring my interface for finding the node. I'll select my skeleton out. This will generate transform object nodes for each of the points in my skeleton, and these will be named based off the names of the points. There is also another thing which I can do in the skeleton node which is not currently part of the network. I'll activate my skeleton node by pressing enter in the viewport. I'll set this to modify, and I can select my points. Here I can give the individual points a point color, and I'll do this for all of my points. I'll then return to my edit graph node. I'll select everything and I'll delete it. I can perform the same operation now. Once again, I'll select my skeleton node out null, and now when the nodes are created, they will inherit the point color. I haven't done this manually yet. We could do this with the color node. We could also add the color as an attribute. However, this is not relevant yet. So we can use this script to add joints from a skeleton to the graph. However, when I try to use my manual skeleton, this will not work. And that is because there are a number of attributes which are generated by KineFX nodes, and some of those attributes are used by the script. So we can use the geometry spreadsheet to see which attributes are generated by the skeleton node. The extra attributes here are the local transform and the scale inheritance. The attribute that we currently require will be the local transform, so we're going to need to add that to our skeleton. The node that I'll need will be under animation, rigging, and the node that we're looking for here is the compute transform node. I'll connect this before my null node which I'm using for the output, and this should add the local transform to my skeleton. If I now try to import my skeleton, it should import correctly. We can now look at the parameters for these nodes, and we can see what these scripts are actually updating. And the value that we're getting updated at the moment is the rest local value. We also have the scaling set to 1. We can import the joints from the skeleton as well. Here we'll get our default transform from the skeleton node. This transform is a lot more random than the transform I generated. If we look at the skeleton, we'll see how the transform is actually being generated. And this transform for the base point is not consistent with the other transforms within the skeleton, and this is why I do manual transforms. We should notice that all the transforms for the skeleton are not consistent with each other. This is not really a good setup for rigging. We can, however, update these points using an orient joints node. The orientation here will be better by default. There are options to modify these transforms, but once again I prefer working with manual transforms. Having updated the transforms for our skeleton, we should now be able to use the update transforms from skeleton script. I'll select the skeleton out node. I'll accept, and you'll see that it will print out our point names. If we now look at the updated node, we'll see that we have a different rest transform. It should also be noted these are local transforms and these are not global transforms. So it will be giving us the transforms relative to their parent joint, not the absolute transform of the joint itself. We should note that with the current version of the script that we are using, we're not actually setting the global transforms at any point. So these are the scripts which come by default, and we can use them to get information into the graph. Next, we'll take a look at how we get our skeleton and mesh into the graph as well.